Tonight we're going to make this fan cover. That's what we're going to call it, using Inventor. We're going to start by creating a new part. The new part's going to be in inches. Some commands are already understood, so I won't get into too many details here. We're going to jump to what is the process of making a sheet metal part. Okay? So when we open up Inventor, we have several different choices in how we build here. And you'll notice when you do File, New, you usually have some choices. Sheet metal versus versus standard. All right? If you look up here. Sheet metal versus standard. Now here's the interesting part. Anyone want to guess what the difference is between these two templates? Well, the neat part is the sheet metal one simply has the sheet metal toolbar active, whereas the standard one does not. Literally, that's the difference between these two. So if you find yourself having started as a normal part file, all the way to the right, you will see convert to sheet metal, and then you'll be in the sheet metal toolbar set. Okay? If you want to start the correct way up front, that's when you go to New and you pick sheet metal. When you hit Create, it already starts you there. That's literally what's different between those two. Do you start with the sheet metal toolbar or not? Yes, I can convert a standard part into a sheet metal part. That opportunity will come on a different day. But for today, we're just going to learn how to make a sheet metal part up front. So here we go. We're going to do all the usual. Basic rules stay the same. Turn on our planes. Make sure we know what orientation we're in. We're in third angle projection. How do I know that? Front, right, and top are legible. They're visible. And the front is not upside down. I know I'm in third angle. This part is third angle projection. It's in inches, so we know that. And then we look at this body, and we see it's got notched corners. It's got bends in it. Doesn't tell us what radius the bends are, though. Do you notice that? Is the material thickness provided? Let me look at the master drawing on this. There it goes. So the material information is given as a note right here. 16 gauge, mild steel, standard, straight relief, flat layout, K factor. Write all this down, guys, because I don't have that on the other drawing. .16 gauge is the material thickness. Now the material thickness that you see is nominal. Nominal means it's average. It doesn't mean you'll never find something a little thinner and something a little thicker with the same reference as 16 gauge. In the real world, nothing is perfect. So please keep that in mind. So if I try to look at like a gauge chart, when it comes to sheet metal, you're going to find out that not only does gauge have a correlation to thickness, that correlation changes when the material type changes. Okay? You have carbon steel gauge. There's 16 gauge, and look at this one. 16 gauge, inches, 0.0598. Doesn't say 0.0625. See that? Proving the point that it's not a static value. Aluminum gauge for 16 is different. 16 gauge aluminum is not the same as 16 gauge steel. Okay? carbon steel. It's not the same as stainless steel. Stainless steel is 0.0625. And there's galvanized steel. That one's 0.0635. And they're brass. Get it? See? They're all different. Copper. Okay? So gauge is not a static value. It's not a constant. That number is different depending on the material you're working with. Now, it says the word mild steel. That's really what it is. Containing small percentages of carbon, strong and tough, but not readily tempered. That's it. It's common steel. When you look at different types of steel, there are 4 types: carbon, alloy, stainless, and tool steel. Okay? Of course, it's a site that wants you to buy material, so it immediately pops up, get a quote. So, when you look at classifications, please go away, thank you. Finishing methods, look at that. Steel numbering, plain steel, resurfaced carbon steel, look at that. It is a science in and of itself. Do you notice that? So when you get into material types, there's a whole bunch of stuff you can read. This looks like a cool site for you to check out on your own, so you can understand materials better. This is called what? Metalsupermarkets.com, types of steel. Okay? It's like cars. You never say, I'm going to buy a car. Well, what kind of car, right? Is it going to be a Buick? Is it going to be not a Century? Is it going to be a Ford? Is it going to be a BMW? What is it going to be? And then it's like, well, which model? And then which package? Got it? In that model. It's the same here. It's not really just steel. So sheet metal, in the deeper sense, is a very involved subject with a lot to it. K-factor, one of my favorite sites regarding that type of content, is when we look up K-factor, Engineer's Edge has a really good site on K-factor. The other site is the Fabricator. There's some really neat information on K-factor. But sheet metal is an involved conversation, if I was going to get into it in depth. Okay? BA, right here, it's not Bachelor of Arts. For me, BA stands for Bendelowens. FYI. And there's math behind it, the K-factor. There's an actual math equation behind it. Remember complementary angle, inclusive angle, all that stuff from geometry class? We use it. So there's a ton of information on sheet metal. And a good site for that is the Fabricator. The Fabricator. Okay? Very good site. The other one I like is the, I wonder if the sheet metal guy is in here. What's it called? Sheetmetal.me. Let's see. It's pulling the same information. There's all these websites. There's so many. Nope, I guess not. Not anymore. It is what it is. But there's Engineer's Edge. And they have a very good section on sheet metal. This is on the same stuff we talked about with gauge, but they also have information on bend allowance equations and calculators right there. Very nice, and I like the way they present it. So if you ever get into sheet metal in a big way, this is the place to check out. Engineer's Edge. And of course, I highly recommend, if you're going to do it, get the, okay, fine, be that way. The Machinery's Handbook is an excellent book to have. It has everything in it, all the kinds of equations you would ever want to know and ever want to use in the world of making anything, I would say. So getting back to this, how do I translate this information to here? So when you look at create, the first thing we're going to do, we're going to create the face. Like, hey, there's no unconsumed sketch. So what do we need to start with? I'm going to make a basic sketch. Now where should I make it? Let's say we make it on the XY plane. We're going to make it, it's square, right? Is this thing square? Yeah, it's 3 by 3. So we're going to do a square. I went too fast, so I'm going to assign the dimension after the fact. So here we have 3 by 3, right? Should be. Now it is. Okay. And we're finishing that sketch. Now we have our basic shape. Now we did 3 by 3. What's 3 by 3? What dimensions is that? From where to where do you think it is, guys? Let's zoom in. 3 inches by 3 inches. Where is that? Is it to the outside of the object or to the inside of the bend? Inside of the bend. You notice that? We have to be very, very careful about that. I can get really, really close, and yeah, it's probably to the inside of the bend. We have to make sure the customer is fully aware of that reality, that we're going to end up measuring this not from the outside. And is it really from the inside of the bend, or is it from the inside of the wall? Inside wall. Inside wall. When you look at it, if I zoom into the other side, this dimension line looks like it's the inside wall. So it's not necessarily the inside of the bend. Because the bend, when you look at it over here, exactly, this bend radius, the center of the bend isn't necessarily that inside wall. So we have to be fully aware of what that means, because how we make our shape is affected by this. We need to make sure it's the right size. So when we see 3 inches, that's to the inside of this dashed space. That's important to remember. So now if I create a face, it's automatically going to pick that face, and that's it. It's not asking us how we want the material assigned. Did you notice that? So you have to think to yourself, where do I really start? You don't start by making the item. You have to first start by setup. Sheetmetal Setup is near the right side. When you click on it, now you have the parameters that we have to work with. So it's default versus default metric. It's use thickness from rule. Well, what rule? What thickness do we want to make it? We'll say from rule, but what material? What is this going to be? Mild steel. So let's see what we have. A, B, C, D, E, F, G. There we go. Mild steel. See that? Now we've got by sheet metal rules, default K factor. So if I edit that, then I'll find out what is the K factor. Right now the default K factor is 0.44. And what did our drawing tell us? 0.44, so we're fine, that's default. The bend radius is the thickness of the material. Now we know the thickness of the material is 16 gauge. So if we look at that, okay, sheet metal rules, see that? Default, here it is. The default thickness. Now annoyingly, let's go back to steel, mild steel. The thickness, it doesn't give us the information by gauge. Do you know that? You see that? Why? Because it varies. We proved that point already. That's why the first thing I did was jump online and say, well, what is 16 gauge? Let's go find out. Well, 16 gauge, depending on the site you go to, is a different number. And depending on the material, it's a different number. And we always have to appreciate the reality is that it's nominal. Okay? Even the number they give you on the chart is not a precise number because the manufacturer, so this, the manufacturer, this is just generic. Carbon steel, 16 gauge, they gave me 0.598. So that's probably more common. Now, what manufacturer on the planet is going to give you thicker than what they need to give you? Right? We all will want to provide it to the minimum tolerance, yes? So that's what we do. Now, notice that that has an impact, a direct impact on dimensions. So you have to understand your product and you have to understand your quality control processes, and whoever your vendor is, whoever's providing you with the material, you have to be very, very clear on what kind of material you're getting. Otherwise, your CAD person, you, will mess up on the drawings. So at your company, before you assume, but typically at a company they'll have these already identified. They'll tell you, oh no, we always get a 0.059 or 060, so this is the number we use. Because typically that's how we have real charts at work. Here in an academic setting, everything's theory. So we're operating on theory. So we're going to theorize that we're going to go with what the handout told us, 0.0625, which to me is like, yeah, right. But I'm going to use it anyways. Okay? I'd want to know. I'd be miking several different inventories of material to verify what really do we get in the company if I was in the field. So here, I'm just going with what I'm told. In reality, I don't ever want you to go with what you're told. I want you to check the material you're using. Because sheet metals, you know, we might say, oh, 0625, 05, blah, blah, who cares? It's a little off. Have you ever assembled something that didn't quite fit? Tolerances matter. Jahai, did you ever assemble something that didn't quite fit? Had to take a mallet to it? Did that happen last week? I had a project that happened last week. So 0625, we're going to go with the default K factor, which we know is we know is yeah. Save the edits. We know it's 0.44, so that's in there. Got it? So we're good to go. Good to go. So the thickness is there. Now we can say, okay, we're good. Everything is good. Now when I go back to face, and I pick this face, I know it should be what thickness? Say again? Should be 0.0625, correct? What we can do is we can go to inspect, we can go to measure, and we check. It says 0.063, but that's simply a factor of it being to how many decimal places? 3. So 0.0625 rounded would be rounded to 3 decimal places would be 0.063. So we know it's good. Cool? So where did I go to check that? Again, remember? Inspect and measure. That's how I got my answer. Go to measure, and then I just click on that edge, and voila. Whoops. I clicked on the very center. If you pick on the very center, it picks the midpoint. So I want to go from end to end. And that's what I get. That's how you verify. All right, it's good. Next. This again is at the 3-inch mark. You have to remember that. We're at the 3-inch mark on this thing, 3 by 3. And our drawing is dimensioned in an odd way. It's 3 by 3. Material thickness is 0.0625. So what does that tell us? Say again? The bend radius? Well, okay, bend radius. That's an interesting conversation. Okay. The bend is supposed to be the material thickness. So what does that mean? Let me see. I'm going to jump over to this object. And the only way I'm going to do this is to zoom in to here and have a conversation about this arc. Okay? Material thickness is this. You have a K factor of 0.44 being applied to this. And the radius, the inside radius will be 0.0625, which is material thickness. What's the outside radius? If the inside radius is 0.0625, which is the natural bend, what do you think the outside radius is? Inside radius plus material thickness. Write that in your notes. The outside radius, the natural bend. When I say natural, I mean you're not forcing it, you're not stretching it, you're not applying a dye, heat treating operation that's changing the material thickness within that radius. A natural bend. Okay? An unforced bend. If the inside radius is material thickness, which is 0.0625, the outside radius, the natural radius is inside radius plus material thickness. In our case, it's 0.0625 plus 0.0625. That's inside radius plus material thickness. So what's the outside radius then? It'll give it to us later anyways by default. 0.125? Yep. Because it's 16th plus a 16th. Correct. So when we look at 3, and now we understand that 3 is to this interior space, what is it to the exterior? I know, I can't draw a straight line worth a darn. 3 and what? 3 and 1/8. Because it's that inside plus material thickness, right? It's 3 and 1/8. Let me see if I can draw a straight line. Ooh, not today. Let's try that one more time. There you go. How's that? See that? Because its inside is 3, plus a 16th on this side, plus a 16th on that side. So 3 and 1/8. So just keep that in your mind. The next step is adding flanges to this. Because as you can tell, this has side walls. It obviously doesn't stop here. It has side walls that go backwards. So when we think about that, that means that the side walls bend inward. When we have create, the way to do that is to add a flange. You can also add a contoured flange. That requires you to have a shape, which is how some people make it. There's some really cool looking loft flanges, which are great for sheet metal, contoured rolls. There's lots of neat things you can make. But for our purposes today, we need a flange. So when I make that flange, I pick the edge, whether it's the top edge or the bottom edge, doesn't matter which. What does matter is that side profile. The side profile matters. The side profile matters. Meaning, are we bending it from the outside, which is what this is, which means the exterior dimensions would be 3 by 3. Are the exterior dimensions of this 3 by 3? Exterior? No. The interior of the flange is 3 by 3, not the exterior. The interior. So we need the bend to be aligned this way, where you see the alignment is outside of base face, okay? Outside of base face. That's where the bend position needs to be. Okay? Outside of base face extents. Got it? All right, guys? That's important. Now the length of that is, shall we say 3/4? Right there? The length of that, we hit apply. Okay, so that's what you get. Now we're going to test ourselves. We're going to rinse and repeat and do this over and over. Let's do this side. Now you see what it does? Do we want it in there? If we say apply, look what it does. See how it notched it? Just for the sake of conversation, we're just going to go all the way around. Then we've got this one. Hit apply, notched it. We'll do the back one. Hit apply. Now what you see is it did a shape with a notch. Now the question, of course, is did you want that? When you look at the front view, did you want the little notch extensions? See that, the notch? Say again? It's not in the drawing, so no, we don't want it. So those are the things you have to watch out for. So when you build the flanges, let me roll it back a bit. You have to appreciate how they're going to react. When you look here, just when we look at this drawing, what do you notice about the bend? It's a little hard to see, I agree. There's the bend interior thickness, and you see how deep this notch is? It goes further into the material. When we did this guy, no, I can't redo, sorry. Let me do it one more time. When you add the flanges, now watch this. I'm going to add all the flanges at the same time. See that? If I add all the flanges in at the same time, remember we talked about the notches, right? Notice what it's doing here. It's saying, hey, what kind of corner do you want? See that image? Where's that corner going to be, right? If I hit apply, see how it's a little smaller. See this? It looks more like this. But what was different? With the last one, I hit each bend and hit apply, each bend independently. Did you notice that? So let me undo. I have to open this up for a minute. Undo. Okay? If I pick all four sides at the same time, meaning when I go to flange and I make sure I pick the correct one, which is this one, I want 90 degrees, I pick all four sides together. Not I pick a side, I hit apply. I pick a side, I hit apply. You will get different results based on how you select your edges. Okay? If I pick all my edges at the same time, I will get different results than if I pick my edges one at a time and apply, one at a time and apply. The results, you can always end up with the same basic shape. It's just how much work do you want to add later. Okay? That's the key. So when I hit apply to this guy and I go to my front view, I get that little extension, equally small bit of an extension, small bit of an extension, small bit of an extension. Notice that? That's what's different. Cool? That's what you have to realize is different. Before I did one, then I hit apply, then I picked another wall, and I hit apply, and then I ended up with a big extension on the one side. So the way the sheet metal sides come out directly correlate with how you select this command. So if you want a clean corner with equal gaps, you got to pick them all together, or pick those two corners together to get this. This, by the way, is a horrible corner if I was going to weld, but that's a different conversation. That's another discussion altogether. Doing sheet metal for the purpose of efficient welding. That's a whole class. That's another conversation. Right now we're taking the simplest form, which is let's just make this sheet metal part. This does not show any welds anyways. This looks like it's all open-ended and just gets bolted like this. But if the customer came back and said they wanted the corner sealed, meaning welded, those are absolutely horrible corners to fill in. I would go back to the customer and say, can we do a compromise on what the corners look like? So I could end up with maybe sharper corners, which allows me for the first look. Remember that first look? When we did the one flange, then we hit apply, and then we did the other flange and hit apply. See how this one was flat and this one had a turn in? This one had an extension to it. If you look at the front, it's still not perfect, not what I want to work on welding, but it's a little better. I would have this thing lapped all the way over to the edge, so I'd have one narrow seam to fill. I don't want a big hole. Okay? To me, that's a big hole. I'd want as narrow a seam as possible so I can minimize the amount of welding, and then of course the complementary grinding that goes with welding to clean up the corners. Those are horrible corners to weld. Never want that. Okay? So next is, but this part doesn't look like it's welded. Next is putting in the tabs. It's got like 4 tabs. I take that back. And they're interesting tabs. They're notched. They're relief. They're pretty neat looking tabs. How do you think we should build those? Okay. If I go to create, we have, let's see, we have flange. But do I want a flange? That we can't have a flange that's the whole length, do we? No. What else do we have? We've got modify, we've got stamping, cutting, corner seam. That's another conversation. That's what, you see that? That, as a secondary step, I clean up the corner. That's what I was talking about before. I don't want big open gaps. We can cut. See that? Ah, what do you see there? Do you see opportunity for this? See where it says cut? So we're going to cut out a notch of some kind. Okay. I'm going to recommend, just for the sake of conversation, we're going to go in the back of this face and create a new sketch. And I'm going to basically build a rectangle, just randomly. No, not that kind of rectangle. I don't want it from the center. I want it from the end. So let's build one from the end. Go this way. What dimension is this thing? We know where it is, which is centered. We know that it's half an inch wide. We know that it is got a I gotta open this up. There we go. Now I can see what I'm doing. I'm gonna trim off this piece of it, trim this off. Okay, this and this need to be what? Tangent. This and this need to be tangent. Okay? We have a center hole, 0.3. Is that what I'm reading? 0.3 diameter, 0.5. Now where is it? Okay, I see the distance. So from center to, whoops. From center to edge, this is 0.3. This needs to be attached to this back wall. So they need to be collinear. So that, all the usual stuff. That's the stuff you know how to do on your own. That's why I just did it. It's not centered. So what I can do is take this plane, take this center, make it coincident. Okay? That's the position that tab, I'll call it. So now if I go back to and finish my sketch and I want to go back to face and I pick this, of all things, I go to create face. And of all things, and they ask me, what am I going to create a face of? And notice what I did. I picked that. I literally picked that. It knew to extrude it out, the material thickness. When I hit apply, look what it did. It created the notch, everything that it needed to make it. That's the reason, by the way, for those of you that are stressing out, gee, what notch do I make that? What size do I make that notch? Anybody sit there trying to figure out, well, I don't have that dimension. How do I get that done? The neat part is, it'll do it for you. That's what I like about the software. Now, being who I am, I've got one down. Do I really want to redo that activity 3 more times so I can get 4? What do you think I should do?
Circular pattern.
Oh yeah. Circular pattern, that's my feature. My rotation axis is this center. I need how many total in the end? 4. I hit OK. Done. And if you're freaking out thinking, oh my God, will it actually do everything? The answer is yes. By the way, this is the power of Autodesk Inventor at work. When people ask me, where is the strength in XYZ product versus XYZ product? Inventor kicks complete anatomy when it comes to sheet metal. That's how straightforward it is. It does not require a ton of finagling to get some beautiful results. They know what they're doing. It's a good product. Okay, there are other products. I won't mention their names, fall on their face, break their nose. Painfully break their nose on certain elements, especially detailing. Well, this is another area where it's good and it's bad. It's got its strong suits. It's getting there. But Inventor, Autodesk Inventor knows what it's. That's very nice for sheet metal. It's a very nice product for sheet metal. Very friendly, very easy. It's intuitive, very intuitive. So I like it. Cool. The next step would be to basically punch the inside out the grate. That's where this image comes in. We've got this absolutely neat-looking, gorgeous-looking, circular pattern. I'm going to give you the benefit of, would you like to make your own punched-out pattern? Who wants to be creative and do a smiley face or your favorite image? Slap through this piece of material. That you could do that. Okay, I'll give you that opportunity. Because you know how to draw circles. You know how to... It's a simple shape. So if you wanted to have a little fun with that face, go right ahead. Okay? The neat thing when you're thinking about, well, how can I be creative with that face? What can I do? One of the neat things I like to talk about is you can always sketch a shape, any shape, onto this face. And it could be any kind of looking shape that you would like to do just for fun. And I'm being extremely random in what I just did. See that? I can be a little more picky, do a letter. I'm still having a little fun with how I did that letter. Finish that sketch, and then that's it. I can just go ahead and punch it out. Now you see this punch tool? On the subject of punching, just for kicks and giggles. Oh, it wants the punch. Okay, I have to draw a punch, a special punch to use it. I'm not going to do that. Instead, I'm just going to old school this and just cut right through it. See this cut feature right here? I'm going to pick that profile and just cut right through it. Now, granted, it was in the same sketch. You notice that? But I only picked the one item, not the other. If I picked both, it would punch both out. That's it. Then the last step. This is nice to do, yes, but this isn't it. What we need is to be able to fabricate this. So we can't obviously fabricate it bent up already because the word bend means that somebody bent it, right? It goes through a bend operation. So what you want to do the last step is create a flat pattern, and that's over here on the end. And boom, it does that for you. The beauty of this flat pattern is this. You see that center line? That's the BA. The bend, that bend allowance line, not the Bachelor of Arts. See? It's a beautiful thing. And that you can actually then scribe into material. You can print it out 101. You can use a etching tool to scribe, especially if it's very precise. You can do that kind of stuff, and you can laser etch where you want things to be bent. There's a lot of things you can do. You can laser cut the whole thing out. Here we're going to have one of those, a plasma cutter in the future, and we will be able to plasma cut out shapes. One of our companies that we interface with, Sureway, that's what they do. They make some really neat stuff, crazy looking things. And that's what they do. They take these drawings and they make real product out of it. And that's the flat pattern of this part. Okay? And here it is right there. And if I just take this piece, this flat pattern, it's a separate drawing, okay? You can actually go through, if you had a specific way that you wanted this put together over on the shop floor, you can literally go through bend operations based on whatever equipment you have in the shop to specify what gets bent when and in what order. Okay? So, and that's it. That is how you would make a sheet metal part using, I gotta undo, yeah. Using Autodesk Inventor. Questions before I turn off the video? Nope. All right. Cool.